Hello everyone, I am Hilson Shrestha, a second-year PhD student at Worcester Polytechnic Institute. In this talk, I am presenting an evaluation study on the use of fairness metrics and algorithms in visualization systems for consensus ranking. Since fairness is a multifaceted concept, a number of definitions of fairness have been proposed over time. As such, a number of tools have been developed which aims to operationalize these diverse definitions of fairness. One popular medium for using these metrics in user-centric computing systems are interactive visualizations. Such visualizations can provide increased transparency across the underlying data and the decision algorithms applied to the data. Recent works on visualizations related to fairness span a wide range of scenarios. They encompass various applications from enabling developers to analyze machine learning model performance to visualization systems addressing graph mining. Additionally, there are visualizations specifically designed to explore intersectional bias as well as those focusing on fairness in ranking scenarios. While these systems exist, efforts combining visualization approaches and fairness metrics and algorithms raise both challenges as well as unique opportunities in this space. Do visualizations have the potential to assist certain fairness-related tasks while hindering others? Is it more effective to visualize fairness metrics by tightly integrating them with the underlying data items, or should they be visualized separately using popular techniques like coordinated multiple views? Could certain visualizations potentially mislead the agency of the users when it comes to promoting fairness in decision-making context? Our work explores these broad questions through a particular instance of a controlled task-based visualization study in the context of fair ranking problem. We took an existing system called FairFuse, which visualizes fairness metrics and provide a fair rank generation algorithm, and compare it against another system called Consensus Views, an equally capable system of manually building a fair consensus ranking, but without visualizations supporting fairness metrics. First, let's take a quick look at FairFuse. Given a set of candidates to be ranked by a set of rankers, such as in a scholarship distribution scenario, where a group of students need to be ranked by different teachers, FairFuse helps build a ranking that best represents all the rankers' decisions, while maintaining fairness in terms of statistical parity. With this overarching goal of building a consensus ranking while maintaining fairness, FairFuse uses recently proposed metrics by Cachel et al. These metrics define the advantage of each group in a ranking, given by favored pair representation or the FPR score, overall fairness measure of a ranking considering all the groups, given by attribute rank parity or ARP, and finally agreement or disagreement of all the rankings made by the stakeholders with the consensus ranking given by PD laws. Given that overarching goal, we then extracted abstract goals and activities from this domain-specific language. These goals and activities led us to the design of the FairFuse system. Now let's quickly look at the major parts of the FairFuse system. Rankings provided by the stakeholders are placed at the left, and the generated consensus ranking is displayed at the right as shown here. On the top of each ranking, we have group fairness view, with each dot representing a group and the position of the dot representing the advantage of the group. Any dots above the 0.5 FPR line represent advantaged groups, and any dots below the 0.5 FPR line represents disadvantaged groups. The difference between the most advantaged and the most disadvantaged groups are colored in gray box representing the ARP score, with smaller gray box representing fairer ranking. The similarity view displays the similarity of any two rankings, with darker square representing higher agreement between rankings. We then built another system called Consensus Views, which is similar to FairFuse, except we removed visualization supporting the metrics. First, we got rid of the FPR and the ARP measure in the group fairness view. We then removed the similarity view. We also removed the slider that controls fairness threshold to auto-generate fair consensus ranking. Now, here is the overall study design. Participants were randomly placed in one of the two conditions. They go through the training phase with textual and video tutorials. Then they enter the study phase, followed by the feedback phase. The study phase was subdivided into two parts. The first part had 8 tasks relating to fairness and consensus, specifically targeting different views of the system. The second part was an open-ended fair rank analysis task, where we provided a new dataset and participants had to generate and manipulate the rankings until they decided that it is fair to all the groups and is also representative of the base rankings. Here are the tasks that were presented to the participants. Each of these tasks relate to one or more of the activities that the system was built upon, which would then link to one or more of the idioms in the system. We can categorize these tasks into 4 groups. Ranking exploration tasks dealt with identifying candidates and their properties and comparison of candidates' position between rankings. Fairness-oriented tasks dealt with identifying advantaged or disadvantaged groups, and consensus representation and analysis tasks asked participants to generate a consensus ranking and identify the most dissimilar stakeholders ranking against it. And finally, open-ended fair ranking analysis task asked participants to build a fair consensus ranking on a completely new dataset. We ran this study with 200 participants in total, 100 in each condition. And here are the results from the study. Results here are presented as a Weining plot with 95% confidence interval. On the x-axis, we have the accuracy, 1 being the correct answer and 0 being the incorrect. Our two conditions are on the y-axis. Let's look at the ranking exploration tasks. Both fair views and consensus views had the same parallel coordinates plot, and we see similar results in all the tasks with no significant differences. But when it comes to fairness-oriented tasks, we see significant differences on all the results. Let's take a look at task 2, which is very interesting. Here we asked participants to identify all the over-advantaged race groups. Note that there were two advantaged race groups. With fair views, participants were able to identify both advantaged race groups, whereas participants in consensus views were only able to identify single advantaged race groups, meaning that if large number of groups were involved, it would have been significantly difficult for consensus views participants to identify advantaged or disadvantaged groups. Third, after generating a consensus ranking, we asked participants to identify the most dissimilar ranking, the consensus ranking. We find that fair views significantly outperformed consensus views. While we expected that this was because of the availability of the similarity view in fair views, the qualitative results told otherwise. We found that participants were hinting their results towards fairness metrics instead of the similarity view. Finally, in the open-ended fair ranking analysis task, where the participants had to generate fair consensus ranking, we found that participants in fair views did significantly better to reduce the ARP score, meaning fairer ranking, while maintaining consensus as much as possible. We also found that fair views resulted in fewer number of interactions to build consensus ranking. Let's take a look at the scatter plot of how the participants performed in terms of ARP and PD loss for each interaction they made. On the x-axis, we have ARP, lower value meaning fairer ranking, and on the y-axis, we have PD loss, with lower value representing less disagreement with the provided base rankings. The circle at the bottom represents the initial consensus ranking that the participants started with in both the conditions. With fair views, we see highly clustered plot with most participants successfully lowering the ARP score. However, when it comes to consensus views, we see very dispersed scatter plot. We should note that some of the participants in consensus views were able to build a fair consensus ranking with low ARP and low PD loss. However, some of the participants completely failed to build consensus while trying to focus on fairness, as shown here at the top part of the figure. Overall results suggest that while both systems are suited for exploring ranking-related tasks, fair views outperformed in terms of accuracy in fairness-related tasks. Based on our study, we distilled a set of 4 takeaways. First takeaway is that researchers developing fairness-aware algorithms should allow end users to adjust the fairness parameters based on specific problem context. Tunable algorithms lead to more satisfactory and appropriate results. Our research shows that while visualization-enabled fairness metrics can promote fairness in decision-making, designers should be cautious about the potential for fairness drift. Blindly trusting fairness can cause decision-makers to miss important societal nuances that the metrics cannot capture. Properly designed visualizations for fairness metrics can help non-expert users navigate complex decision-making tasks involving bias mitigation. Some participants in consensus views were meticulously changing their rankings to make it fair. We can see that by the number of interactions they make, which is not the case for fair views. And finally, inappropriately designed fairness metrics visualization can lead to incorrect conclusions. The way in which fairness metrics are presented should be carefully considered by visualization designers. Otherwise, users may overlook important information and achieve an incomplete understanding of the task at hand. Our study comes with certain limitations. First, fair views only uses 2 fairness metrics within the widely accepted definitions of group fairness in the fairness community. It also considers 1 tunable algorithm for generating fair consensus ranking. The fulfillment of the goals of the system relied on those metrics in the task abstraction phase. Future work could explore the effect of providing multiple algorithms and metrics to the users. Finally, we only considered a limited number of groups and a single protected attribute for the study. Future work could extend on including multiple protected attributes and their intersectionality. Thank you.